Welcome everyone, and thank you for joining us today for our webinar titled Supervised Graph Machine Learning now in Neo4j. My name is Sabine Seitz. I'm part of the marketing team here at Neo4j, and today I'm joined by Amy Hodler, Graph Analytics and AI Program Director, and Dr. Alicia Frame, Lead Data Scientist at Neo4j. We have pre-recorded the session so that both Amy and Alicia are available to answer your questions throughout the webinar. So please submit your questions using the questions tab located at the top of your screen. We will publish all questions. They will be all visible to you after answering. If by any chance we don't get to answer all of your questions, mail them please to webinar@neo4j.com. Also, you will receive a follow-up email with the links to the slides and the recording. And with that, I'll go ahead and hand it over to Alicia and Amy.
Great. Thank you for that great introduction. Thank you.
Well, let's get started with just kind of a quick level set in case you're joining us, from a different place. Let's take a look at what graph data science is to start with. So if you think about graph data science, it's really the same data science that you probably know and love. It's just that you're analyzing relationships and the structure of the data itself. And if you think about it, you could be talking about graph queries. You could be talking about graph algorithms, combining them to maybe do some feature engineering. You could be trying to explore your graph with visualization, so with the Bloom tool that Neo4j has. So there are very different ways that you can kind of combine what you're doing, what you may traditionally think of as statistics or data exploration, but combining them together to in a multidisciplinary form to try to answer some kind of questions you might have or make a prediction. The other thing that I just wanted to share with everyone, we're kind of excited about this. We've been doing some analysis of our own community, and what we're seeing is that we know that graph data science and graphs are being promoted heavily and used heavily in AI research papers, and that's the chart at the above. And you can see over the last couple of years, it's kind of exponentially, almost exponentially grown. That we're seeing this explosion of interest in combining graphs and AI, and that makes a lot of sense because graphs have a lot of predictive elements in them. But what we didn't realize when we looked at our own community is that it's also exploding in interest within the Neo4j community. So the Graph Algorithms book we put out not quite 2 years ago, but it's already exceeded 160,000 downloads. So a lot of interest from you folks that are joining. But we've also looked at the traffic on the Graph Data Science web pages and the data scientists that are in our database, our own community. And in the last half, so second half of 2020, it actually increased 4 times the traffic on our website for the data science area and 3 times the increase for actual data scientists in our database. So we're really quite happy and excited about the interest that you guys have, and appreciate all the feedback as well, because that's how we all the new features that we talk about, those come from our community and you guys using them. And then just a quick note about the market in general. So it's not just us, it's not just you that are joining, that are noticing how graphs and machine learning go together and graphs and analytics go together. Gartner as well is starting to talk quite a bit about graphs. There's a recent top 10 trends in data and analytics that Gartner put out just a few weeks ago that talks about how graphs are the foundation of modern data and analytics. And they also talk about how the use of graphs in AI changes significantly depending on how mature the organization. So if you have a very mature data science practice, they're saying that at the highest maturity, we're seeing 48% uptick in use of graphs in machine learning and AI where the maturity is high. So anyhow, so thank you for your support and your questions. Keep them coming. We love them. And if you are new to using data science and graphs together, one of the things that we talk to a lot of people about, or I think it's the big aha moment for people, is the use of relationships. So that's basically what graphs are. They're, focused on relationships. And the use of relationships, because relationships are very predictive of behavior. We see that over and over again in research papers. There's a great book called Connected about it. But the interesting things, you may realize that relationships are very predictive of behavior. It makes sense. But if you can't see those relationships, you really can't use them. You can't analyze them. And a lot of data science ignores relationships because they are difficult to put into a machine learning system, especially at scale. They're difficult to wrangle them, put them in the right format, and then use them to make predictions. But graphs, since they're built using relationships, you don't have to try to guess at some correlations. You don't have to try to figure out where the relationships are and then format them properly. They're already inherent in the data you have. And so that's why a lot of people use graphs and data science together. And the other thing that I like to talk to people about is, if you're excited about using them, you can use them in a very many different ways. And so I think about the workflow of graphs and AI, or graphs and data science. And normally you're trying to, source some data, then you're trying to build some models that reflect your business. Then you want to do some analysis of the results. Are they actually correct? And then you want to put them in production and get some value out of them. And graphs can help from beginning to end. So at the very beginning, we can look at knowledge graphs. If you're trying to source your data, you want to make sure that it's trusted. You know what the data lineage is. If you can't trust your data, you certainly can't trust your model later on. And then when you're building your model, of course, you want to build predictive features. So you can use graph feature engineering to do that. And then you want to, as I said, analyze it. And if you're in the analysis stage of your predictions, you want to be able to do counterfactual searches. Is the predictions actually, does my data, does my knowledge graph actually reflect what my predictions say? Can I find things that are, that can prove myself wrong? And then when you want to capitalize it, there's many different ways to do that. It's all about integration. But another way that we see people do using graphs, knowledge graphs in production, is using a knowledge graph to help an AI make decisions as well. So kind of a contextual AI. So various different ways you can use graphs in data science and machine learning. But what we're going to talk about today is more around the modeling and machine learning modeling, and kind of focus in that area itself. So I think, Alicia, if you can tell us a little bit more about what's in Neo4j to help with that, that'd be great.
Awesome. So I kind of like to start off with, hopefully we've gotten you excited about graph data science. You're like, okay, how do I use relationships? And really the question that we need to answer next is, if you want to use relationships, what does Neo4j let you do? And I like to think of kind of three parts of our connected data science platform, right? At the heart, you have the Neo4j database that we all know and love. And this lets you store your connected data in a graphy shape. So you don't run the risk of corrupting your data through ETL pipelines, through tables. So you can query your connected data and kind of do pattern matching, right? Thinking back to that Venn diagram at the beginning, right? A big part of graph data science is just being able to interact with your connected data and ask questions. So on top of the database, we have on the left side, the Graph Data Science Library. It's a data science plugin that runs with Neo4j that contains scalable graph algorithms, graph embeddings, supervised machine learning pipelines as of our 1.5 release, as well as the analytics workspace, which lets you transform that graph in your database into different shapes, snapshots, permutations to test out and experiment with different predictions and different data sets. And then on the other side, we have Neo4j Bloom. We talked about in that Venn diagram, the visualization part. So Bloom and other tools like Linkurious let you interact with your graph data. It lets you visually explore and prototype, explain to your colleagues, give a presentation on, do a sanity check on your data in a really easy to use, friendly way. And kind of taken together, these form kind of our graph data science platform and help you start reasoning about relationships. So what is in the Graph Data Science Library, right? We talk about it, you hear GDS, what does it do? There's really kind of two pieces. One is the algorithms, and one is the graph catalog or the analytics workspace. The algorithms are kind of usually what people think about first and foremost. These are the different unsupervised machine learning techniques that let you find patterns in the graph. So that's things like pathfinding and search. So given two nodes, what's the shortest path between them? What's the optimal path? How many nodes can I reach from this node? And we see those used a lot in supply chain and logistics or route planning, or even as predictive features. The closer two nodes are together in a graph, the more likely they are to be linked. We have the community detection algorithms that, if you're familiar with kind of clustering on your tabular data, it's pretty similar to that. You find the parts of the graph that are more connected to each other than the rest of the graph. These are algorithms like Louvain or weakly connected components. We have the similarity algorithms that let you say, given two nodes, how similar are they based on, say, their neighboring nodes, or the attributes of neighboring nodes, or the attributes of their relationships. And it lets you say, you know, I have this node, I know that they've committed fraud. What's the most similar node in my graph to that node? We have the centrality and importance algorithms that let you say, you know, given a node, how important is it? And you see that a lot when you're looking at folks doing influencer or risk identification, who's most important, or search optimization, right? PageRank is kind of the first graph algorithm that comes to mind. It's a centrality algorithm. It was invented to help you sort through web pages. We have the link prediction algorithms, and these are different from the link prediction we'll be talking about later in the webinar. These are kind of these heuristics that, given a pair of nodes, can give you a probability of forming a relationship based on some predefined rules. So an example might be common neighbors. The more common neighbors two nodes have, the more likely they are to be connected. And so these are kind of simple heuristics that can help you find missing information. And then we have the graph embeddings, which let you learn from your structural information in your graph to come up with a representation of your graph that you can use for machine learning. So it's basically a lower dimensional representation of your graph that connects all that information, that extended topology, all those features we just talked about, like how important is this node, what community is it in? But it collects that information up in a machine readable representation, basically a vector of a set length, and then you can do machine learning with it. And we'll show that later in the demos. And while these are kind of the things that first jump to mind, right, the algorithms, we also have the graph catalog and the analytics workspace, which is kind of our secret sauce. And that's what lets you take your graph in your database and transform it or subset it. It's highly optimized for these graph global computations that we do in the GDS library. So it lets you run things in parallel, super fast on lots of data. But also it lets you transform your graph. So maybe I only want to perform ML on this subset, or I want to see what would happen if I, instead of having people like places, people like the same places. I can create new relationships in memory and transform my graph. And kind of taken together, those let you do data science inside Neo4j. And as of our 1.5 release, we've added in supervised machine learning that can leverage these algorithms and leverage the graph catalog to help you train predictive models. So I like to kind of zoom in on the difference between queries, algorithms, and embeddings for folks who kind of haven't encountered this before and really aren't used to thinking about the differences. So queries, if you've used Neo4j, or even, you know, we've all used SQL before, right? A query is human crafted. I know there's something I'm looking for, and I want to pull those results back. In a graph, it's pattern matching. So in my example, I have match a person and an enemy of that person, and then that second person's enemy, and then take the first person and the third person and make them friends, right? The enemy of my enemy is my friend. So I write that query based on some domain knowledge, and I know exactly what the result is. That's kind of the foundation of working with graphs, pattern matching. Building on top of that, we talk about graph algorithms. These are predefined formulas like PageRank, where you have a way of taking your graph and running some kind of calculation on it. So here we've got the formula for PageRank. For every node, you add up the centrality scores of its adjacent nodes, you iterate over the graph, and you get a human readable result. So Emil, our CEO's PageRank in my imaginary example is 13. My PageRank is 4. And so I know that a higher PageRank means someone is more important. So Emil is more important than I am. There's a predefined formula, but the result is directly interpretable. Then kind of the next level up is embeddings. And so this is an AI learned formula. It's not like we always add up all of the neighbors of this node and repeat until stable, right? There's some kind of algorithm that's defined for how do I learn the representation of this graph. And then it gives you a machine readable result. So if I have, this is a very small screen grab of, I believe, GraphSage, which basically says, here's the way you learn the representation. Collect up the neighbors, collect up their attributes, fit a loss function, and learn the correct representation. And then once I've done that, I get these vectors. And if I look at them, I see that Emil, Amy, and I all have the same length vector, but it doesn't mean anything. But if you put it into a supervised machine learning model, or even something unsupervised like cosine similarity, we've learned to represent the graph in a way that we can reason about it and make predictions with machine learning. So we kind of move up in complexity and kind of level of human involvement, from queries that are handcrafted to algorithms that are human interpretable to embeddings where you learn the representation of your graph for your problem, and then you pipe that into some kind of ML process. Part of this is, so we talked about embeddings. This whole webinar is about supervised machine learning and Neo4j. We talked about what is in the graph data science library. Something that we've added as of the 1.4 release and improved in the 1.5 release is our model catalog. And we're really excited about this. So what this is you can now train a supervised machine learning model in Neo4j. So just like you would do in scikit-learn, model.train, model.predict, we support the ability to train models in Neo and then apply those models to unseen parts of your graph or new data. So sometimes if you've attended a lot of Neo4j stuff before, you'll hear us talking about data modeling when we mean schemas. What these models are predictive models. They live in a model catalog inside Neo4j. That model catalog contains versioning information about each model. What data was this model trained on? What type of model is it? Who created it? It's got timestamps, it's got model names. You can manage multiple models. And as of 1.5, some of your models can be published, stored, and loaded from disk. So if you've spent, 6 hours training a GraphSage model, you want to use that down the line, you can persist that model to disk, load it up, and it'll be available even if your database restarts. So we're pretty excited about this new feature. I've kind of been leaving little breadcrumbs about all the new features in 1.5 that we're excited about, but we do have one slide that kind of summarizes all of it. This was a pretty big release, so there's a lot to be excited. We have graph machine learning workflows, and that's what this webinar is about, right? Using supervised learning in Neo4j to train a predictive model that you can apply to your graph. Those models can be persistent and publishable. We support node classification and link prediction. But that's not all that was in this release. I mentioned pathfinding, and we talked about the different algorithms. We spent a lot of time improving our pathfinding models. So we've got a new standardized API. All of the supported pathfinding algorithms will return paths now. And we've improved the performance, so they're about 25% faster. For our Enterprise Edition users, we've introduced a new memory compression format. So a new way of storing that data in memory in that analytics workspace that uses up to 75% less memory. So if you are on a resource restrained system, maybe you have 30 people trying to load graphs at the same time. Maybe you can't get a bigger box, or maybe you have a really, really large in-memory graph. This lets you store more in memory and reason about it faster. And then finally, last but not least, we've also introduced 2 new algorithms in this release, different from the supervised machine learning workflows. We introduced 2 more classic graph algorithms, speaker-listener label propagation, which is a multi-community community detection algorithm. So if you've got overlapping communities, speaker-listener LPA, which is a tongue twister, lets you find nodes that are in more than one community. We also introduced, at your request, the HITS algorithm, or hubs and authorities, which is another kind of centrality algorithm that has 2 different ways of defining importance. You have hub nodes and authority nodes, and you get 2 different scores. Along with those, we've made some improvements to Pregel, which is how we implemented them, and a whole lot more. But again, today we're really going to be focused on the graph machine learning workflows. So I keep talking about supervised machine learning. I think it's really helpful to kind of take a step back and talk about when we talk about machine learning, what do we mean, right? And typically you think about, you have your unsupervised machine learning when you don't have any labels, right? So your data is unlabeled, you're looking for patterns. It's really data driven. So you have this data, you want to find ways of reasoning about it. So you can do things like clustering. So let me group data together that's more similar. You could do association. So everyone knows market basket, association rule. These two things are commonly seen together in my data. Or dimensionality reduction, like PCA, right? Where you want to make generalizations about your data. And this is all, not reliant on having labels. This is really what we've talked about in the past with graph algorithms. On the other side, we have our supervised machine learning, which is what we mean when you say, I want to train a model, right? You have labeled data and you want to predict something about it. You can predict a number, regression, or predict a category with classification. So this is really task-driven. It's labeled data and you're predicting values. When we talk about kind of graph algorithms in general, those fall on the unsupervised machine learning side of the house, right? So community detection algorithms are clustering on a graph. Similarity and pathfinding are association on a graph. Dimensionality reduction, you can think about centrality as a way of summing up each node with a single number. Or the unsupervised embeddings is a dimensionality reduction technique, something like FastRP. And that's kind of the traditional graph algorithms. But in this release, we're kind of moving into supervised machine learning, letting you leverage the labels you have in your graph to enrich your data. So to spend just a moment for folks who don't spend all day thinking about this, supervised machine learning is when you use labeled data to learn a function to map input data onto output data. So in our little toy example, you've all probably seen something like this before. You have pictures, right? And they're labeled, right? I have, this is a picture of a cat, and this is a picture of a dog. And I'd have lots and lots of labeled pictures. And then you would pass those into a model. And the model would learn a function that would take that picture and predict, is it a cat or is it a dog? And so I have some kind of mathematical function that takes the information about each of these pictures. So what color is it? How big is it? These are images. So all kinds of cool features. You take those features, you figure out, how do I classify cat or dog based on those features? And then the whole reason we've trained the model is we can put in new data to those functions that we've learned and make a prediction. So I have this new data. I don't know what the label is. I've trained my functions and they can say, this is a cat. The problem with supervised machine learning is you need to measure if it's good or not, right? I could have a model that says everything is a cat and it is a model. My function is, if true equals cat. You want to hold out some data where you know what the labels are, and then test your model. And basically you want to say, I know these are cats. Can my model predict that they're cats? Okay, I choose the best performing model. So what we're doing in Neo4j now is letting you use the labels in your graph to train models to make predictions about your graph and evaluate how good those models are so you can then apply them to new data. And so with this, I'll pass it back to Amy.
Great, thank you. So you're probably wondering at this point, so what types of supervised machine learning can I do now? So we're really excited about it, but what can I do? So there's two types in quick summary: node classification and link prediction. But I think it's important to emphasize something Alicia talked about is the labeled data. So you need to have labels on your data, and basically think of it as pairs of nodes, that might be either linked or not. And how are they categories? What are the labels on them? If you're thinking about like a fraud example, maybe the label is fraudster, and then you have another label that says is not fraudster, and you can use that to learn things on. But you also have features as well. And so that could be pre-existing attributes. So maybe there's information about what kind of a customer this is. Maybe there's some pre-computed value that you have, like a page rank value. Maybe this is a high page rank customer. They have they perform a lot of transactions with you. Or maybe you don't know what you're looking for and you've created some embeddings. So there's different features that you may have in your data as well. And as Alicia showed on the last slide, you use those, the labels and the features to compute some kind of function that can then create your model and predict something. In the case of node classification, you're simply trying to answer, like, what kind of node is this? What kind of label should it have? What kind of category should it belong to? Fraud, not fraud. And in link prediction, you're trying to understand whether there should be a relationship between two nodes. And so it's either maybe a relationship you haven't seen yet, or a relationship that you predict is going to form in the future. So those are the two basic types. And to take a little bit, double click at both of these, we can start with node classification. And again, that's about trying to predict the label or the categorical property. And I used fraud before, but it could be something like churn prediction. So you might have nodes that are labeled as customers that have churned, and then maybe ones that have been loyal for a long time. Maybe anybody over 3 years with you is considered a loyal customer. And you need to load that data into memory with the labels and the features you want to use. So maybe you also want to use a feature such as what community are they in, and are they in a community that has other people who have churned? So that could be an indicator. And so you load your data with the features that you're going to use, and then you specify what you want to use to make those predictions. So maybe you've decided to use that community ID, or perhaps you're using just the PageRank score. Does somebody have a high centrality, or you're using an embedding, and maybe those things are predictive. So you decide what you're going to use to make those predictions, and then you simply use in Neo4j the node classification.train function. And what comes out of that is a predictive model in your catalog. Now I'm kind of skipping, you can kind of notice to the left there, all of these other things that happen in the background. And that's kind of why, that's one of the things that I get excited about, because it's really easy for me to make mistakes. And I like the fact that Neo4j automates the hard parts. And so it will do a split between your trained data and your test data. And that's really important because to do that split properly, because in graphs, it's very easy to have data leakage because everything's connected. So having that train test split for you and having it automated is something that I think is a very humane thing for engineers to do, for people like me. And then what Neo4j actually builds a logistic regression models using that training data and the parameters that you previously specified, community ID, maybe a centrality score, maybe an embedding. But it's going to use that information to predict the correct label. And then it'll evaluate the accuracy of different models based on your train and your test split. So you can test your accuracy. And then it returns the best performing model based on that logistic regression and puts it into your model catalog with a confidence score as well. So that's kind of the flow that happens. And like I said, it looks really simple at the top line, but there's a lot that's being automated, thank goodness, in the back end to make sure that the predictive model is done accurately. So I think Alicia has a really cool demo for us on this. I'll turn it over to Alicia.
Awesome. So let's do some hands-on and see what this looks like in Neo4j. So let me just switch so that you all can see my screen. And what I've got here, and this is all actually available on my GitHub, so if you want to pull this down and play with it afterwards, feel free. I've loaded the Marvel Universe graph, so everybody loves superheroes. What's in this graph is we have our characters, so X-Men, Agents of S.H.I.E.L.D., all that cool stuff. Every character in the Marvel Universe is a node. They can appear in comics or be part of events, and the events can happen in comics or movies. And these characters are part of groups, and the groups are things like, is an X-Man, is a Agent of S.H.I.E.L.D., is, now we're testing my knowledge of Marvel, are they Guardians of the Galaxy, right? So characters can be in groups. Each character has different statistics about how strong they are, how smart they are, how fast they are. So all this rich information. And what we're gonna do is we're gonna start by just training a node classification model. And so there's some things I did beforehand just to make this easier for us to work with. that I'm not going to rerun, but I do want to kind of show you what I'm doing. So one of the things I did is we go in and we do some feature engineering. So I create features, not just the statistics that are loaded in already, but I want to create some graph-based features. So I'm going to just show you the commands that I ran. And what I did is in my in-memory graph, I loaded my data in, and I generated a whole bunch of different features that might be predictive, right? I generated my page rank of my Marvel character graph based on who was an ally of who. I also calculated page rank based on who appeared with who. So this is, I talked about the secret sauce of the graph catalog and the in-memory graph, where I can reshape my graph and test out different shapes. I loaded a graph in memory. I loaded a whole bunch of different relationships I wanted to play around with. And then I can run PageRank on different relationships to get different values. And I ran PageRank. You can see here, I've run between this centrality, and I ran the hits algorithm, which is that new algorithm that we've talked about, hubs and authorities. And what's neat here is you see that unlike betweenness, where you just get a single number for each node, you get an authority property and a hub property. So each node gets 2 different centrality scores. I'm not going to rerun this because we don't want to sit and watch it churn. I ran that, and then the next thing I did was I computed a graph embedding. So we talked about embeddings are a way of summarizing your data. So I'm going to just give you a peek of what it looks like to run a graph embedding. And so I ran FastRP extended, which is a type of embedding based on kind of matrix multiplication. It's super fast. It's like 75,000 times faster than Node2vec. And we have an implementation that also learns based on your node attributes. So remember, I went in and I added all these new properties to my graph. I added PageRank, I added betweenness centrality, and each of my characters already had things like strength, fighting skill, durability, speed, intelligence. I had that tabular data. So I can tell FastRP extended to take my appeared with relationship and all of these feature properties that I want to learn on, and learn an embedding based on both my graph topology and those features. And I will say that beforehand I did some tuning, but you can change different hyperparameters. Like, do you want to use relationship weights? Do you want it, how long is your embedding? Is it 250 characters? Is it 500? How many dimensions of that embedding do you want to reserve to represent properties? How many weights do you want for each iteration? And then I can save that back to my graph. And so I did that beforehand just to have my feature engineering kind of ready to go. What we're going to do is jump into the work for node classification. So the first thing I want to do is go in and select and label the data that I want to use. So if I go in, and I'm going to show you what I did here. So there's a couple things we want to do. Remember, we have to learn a class for a node. So we want to find some kind of category. For this example, I'm going to predict if characters are X-Men or are not. And I went into the graph and I checked beforehand, and I think there are 41 individuals labeled as X-Men. But thanks to my Googling skills, I learned that there are over 100 X-Men in the Marvel universe. And I confirmed that we have some unlabeled X-Men fighting in the graph. So what I'm going to do is I'm going to set the label on my characters who are X-Men. If they're part of the X-Men group, they get is X-Men equals 1. And I'm labeling them as model data. I want to use them in my predictive model. The next thing I'm going to do is I'm going to go in and I'm going to find some people who are not X-Men, right? Because I need a positive sample and a negative sample. So just like with our cats and dogs, if you want to predict a cat, you have to have some things that are not cats. If I want to predict an X-Men, I need some things that are not X-Men. And so I'm going to find characters that are not part of other groups. So they're not, you know, Agents of S.H.I.E.L.D. or Guardians of the Galaxy. They're unaffiliated. And I'm going to make sure that they're not appearing with X-Men. Because if they're appearing with X-Men, they're pretty likely to be X-Men. I don't want to like cheat in my model. And then I'm going to say I don't want any orphan nodes. So I'm going to say the degree of my nodes has to be greater than 0. And what's in here where I say rand is less than 0.13, I'm actually rebalancing my data. So I know there are about 40 X-Men. I know there's about 1,500 unlabeled people in my graph. I want to make sure I get about 40 X-Men and 40 not X-Men. And this is just class rebalancing, because if I have 40 X-Men and 1,000 not X-Men, I will train a really good model that will predict that no one is an X-Man, and that's not helpful. So I need to go in and rebalance my data. And so I've chosen my negative samples. I set is Xman to 0, and I set the label to model data. And then I'm going to label some holdout data that's not model data that I'm going to use to make predictions on. And so I'm going to just run these 3 queries back to back and basically set up my graph to be able to do some machine learning on it. And so what we'll see here is as soon as they finish running, they're going to pop up to the top. And you can see those are done. And so next I want to go in and load my graph for predictions. And so what you can see here, and this is, I talk about, we can load different slices of data into memory. I'm creating my Marvel model data graph, and I'm going to load in characters that have been labeled as model data. Remember, I labeled my is Xman and is my not Xman, and I gave them a model data label. I'm going to label, and I'm going to load some properties about them, right? I've got my FastRP embedding that I already trained, and then I have these tabular properties that I could use as well if I wanted to. I also am going to load in my holdout characters. And the reason I'm doing this is because I don't want to have to load my data twice, right? I can load my data in to train my model. And then when I want to look at the predictions, I can just run on the same graph on top of the holdout data. And so I'm going to just hit run and pop this back in. And this is going to run pretty quickly. And then you'll see kind of how much data I've loaded into memory. As soon as it's done, minimize this. So you can see I've loaded in about 1,000 nodes. So in my model data and my holdout data, and 65,000 relationships between those nodes. So the next thing I want to do is I want to train my node classifier, right? We spent all this time getting my data set up. I'm going to go in and I'm going to do my model.train. So what this looks like, and this is probably what you're all excited about, is here's the syntax, right? I want to call gds.alpha.ml.nodeclassification.train. And I'll specify the graph I want to run on, which is our Marvel model data. The node labels I want to make predictions on. So that's our characters. And remember, I have my holdout characters as well. So I'm not using those. I'm going to name the model that I'm training. So this is my Xmen model FastRP, because the only feature I'm giving it is this FastRP embedding. And the target property, what I want to make predictions on, is Xman. So I want to predict who's an Xman, who's not. And then these kind of next 4 pieces are really about my model performance, right? So how do I measure if my model is good? I'm going to use my F1 weighted score to decide which model is best, but I'm also going to return the accuracy of my models. Holdout fraction and validation folds basically handle internally how we do our cross-validation as we're generating different models. And then in the params section, what I'm doing is I'm saying I want to build a whole bunch of logistic regression models with different combinations of hyperparameters. So I want to have different penalties and different max iterations and pick the model that's best. When it's done training a model, it's going to yield the model info. And to make it easier to read, I'm just going to be returning the winning model, the train graph score, and the test graph score. And so let me make this small again and then click run. And what this is going to do is it's going to train that model. It's going to train a whole bunch of models and pick the best model. So the best model out of all the models I trained has a train graph score of F1 score of 0.65, not too bad. Test graph score of 0.81. So I've trained a pretty decent model. You will probably in real life need to do some tuning of your embeddings. Your first try won't work, but this tested all the different models, picked the best one, and now has put it in my model catalog. So what I can do now that I have a model is I can apply that model to some data, right? So I have my holdout data that I talked about before, and I've got my Xmen model FastRP that we talked about that's saved in memory. And I've got my mutate property. So I'm going to add a prediction to my graph if I've predicted that this unlabeled character is or is not an Xman. And I'm going to go ahead and just run this. So I'm using the model that's in my catalog. I'm applying it to my in-memory graph. It's going to run pretty quickly and make some predictions. So I can see that I think it's finished. There we go. So the 2 green check marks mean it's done. And so now I want to check those predictions, right? So I've updated my in-memory graph with my predictions. I'm going to stream them back so I can see what they are. So I'm just going to check. I've made my predictions. I want to see where something was not an input to my model, and they've been predicted to be an X-Man to kind of see how it worked out. And so this will run and give me a list of the folks that we predict might be X-Men based on the graph data and the probability that we think they're X-Men. And so what I see here is, the first one on my list is Steve Rogers, Captain America. He's not an X-Man, but he interacts with X-Men a lot. So if we're learning on the graph topology, it makes sense. And if we kind of go through this list, we see a lot of agents of S.H.I.E.L.D. who interact with the X-Men a lot. But if we scroll down, we should find some new X-Men. So I happen to know, thanks to the wonders of the internet, that Beast is actually an X-Man. He's not labeled as one in the graph, but we've successfully recovered an unlabeled X-Men. And we can see with the probability that there's a 55% chance that we have correctly identified. That's our level of confidence. So 55% chance that Beast is actually an X-Man. So we've trained a model in Neo4j, applied it to new data, and made some predictions to find X-Men. So with that, I'm going to pass it back to Amy to talk about link prediction.
Awesome. Thank you. And I was thinking, as you were talking about the probability, you could then run other analytics. You could write back the probability of the prediction and then do other analysis and exploration based on the probability score. So very cool stuff. To shift to link prediction, the other supervised machine learning that we have in Neo4j, that is, just to reiterate, that is about predicting things that relationships you haven't seen or that will form in the future. An example might be predicting whether a customer, might buy a particular product, or maybe if I can think about an X-Man example or a Marvel example, and I don't know what Alicia is going to show, so it'll be funny if this is correct or if this is what she's going to show. But you might want to predict that a couple characters were going to be in the same comic book together in the same issue or something like that. So it's kind of the classic collaboration citation, but maybe you want to say, hey, these two people, these two X-Men are going to go on an adventure together. And you would have to have, just like we said with the other example, you'd have to have both positive and negative examples where they weren't in a comic book together and where some people were. So you'd have to have both those types of examples. So just like with the node classification, you'd want to load that information into memory, then do your split between train and test, kind of have that holdout information, and then use link prediction.train. So with this one, this is, again, automating a lot of the tricky parts, building that logistic regression model, using your training data and any parameters you might have included in there, and then trying to predict the label. So, and just like the other example, you can, look at the confidence score of the prediction that is included in the model catalog. So very similar to a lot of the steps, but in this case, you're doing a different type of prediction, trying to understand whether there should be relationships, whether there are citations in the future that are in common. And I hope, Alicia, you're going to talk a little bit about how to deal with the either a very sparse or a very dense graph, because I think that's something that comes up a lot when we talk about link prediction. So I guess with that, I'll very quickly get this back over to Alicia so that she can show us some other cool demo.
Awesome. So Amy kind of spoiled my secret. I'm going to predict who's going to be in the next X-Men movie or comic book together.
I got it right.
I think the fun thing would be thinking of other things to predict about relationships with X-Men. I guess you could predict who's going to be an enemy in the future, or I don't know, new events. If we have a new event, who's going to participate? But Amy kind of got my simple use case, which was who is going to appear in the next X-Men comic book or movie together. So the first thing I do is, just like with node classification, I kind of labeled my data so that I could rebalance it, so I could figure out what am I learning on, what am I holding out. So the first thing I'm going to do is I'm going to go in and split my graph. I'm going to say, I'm going to take X-Men information from 2016 to present, and I'm going to hold that out. So I'm going to say, find me the characters that are appearing in comics together from the year 2016 to the year 2020. If they are not appearing in those comic books together, so if they're appearing together before 2016, I'm going to label them as appeared with for model, right? So the number of times they appear in the comic books together pre-2016, that's the relationship I want to use for my model. So they've appeared together in the past. And I'm basically time slicing my data so I can hold out 2016 to present when I want to make predictions. And so I'm going to go and do exactly the same thing as I did with my other set where I had my model data and my holdout data. I have my model relationship and I've got my holdout relationship. And so these are just two super simple Cypher queries that I run to kind of rejigger my graph to make some predictions about links. This is going to run pretty quickly. And as soon as that finishes, we're going to do the same thing we did before and load that data into memory to learn on. So remember, we talk about our secret sauce is the graph catalog. So this time I want to load in the slice of my graph that I use for making predictions on it. So let me show you the content here. So what does loading this graph look like? What I've loaded in is I'm calling my in-memory graph, my Marvel link prediction data. I'm loading in my characters, and I'm loading in these fast RP embeddings. I'm going to actually comment this one out because it is not in this graph. And I'm loading, kind of the same information I had before that I can use to make predictions. But the difference is for link prediction, internally, what we're going to be considering is each pair of nodes and whether they should appear together or not. So I need to load in all of my nodes and all of my relationships. And just like before, I didn't want to load two graphs. I'm going to load in my appeared with model and my appeared with holdout in the same graph and just reference them separately. So let's go ahead and run this. Shouldn't take very long. And as soon as it's done, we'll have that in-memory graph. We'll have another one to learn on. And here we go. We've got 1,100 nodes, 54,000 relationships we're going to be making predictions about. So the next thing we're going to do, and Amy already kind of touched on this, is test train splits are hard. So we've actually added some procedures into GDS to handle splitting your relationships. And the important thing to remember is just kind of the sequence that we want to run them in, right? So you want to do split relationships, and we're going to mutate our in-memory graph. So remember, I loaded my Marvel link predict data graph, and I have my appeared with data that I want to use for my model. And what I'm going to do is I'm going to take my appeared with relationship, and I'm going to split it into my test graph and the remaining data. And then I'm going to split it again, and I'm going to take that same data set. I'm going to take I already kind of chunked off my test graph. Now I have my remaining data, and I want to chunk off a train graph. And so this is, I'm saying, okay, here's my test set of relationships. Here's my train set of relationships. And I have some that I'm going to ignore for training, kind of a holdout set. And the important thing to know here is what we're doing internally is we're splitting the graph into test and train. And you're going to use your train graph for that cross-validation step. But we're also internally creating those negative and positive relationships. So when we talked about the node classification, I had to go in and set, this is an X-man, this is not an X-man. We're doing the negative sampling ourselves internally, so you don't have to worry about it. So let me go ahead and run this. And then as soon as it's done, it'll update my in-memory graph. I can shrink it back down. We'll just wait on the green check marks. As soon as browser responds, I think it means it's finished. So here we go. We've split our relationships. They're mutated. So the next step, so we've got everything set up. We're going to train our model. So I'm going to show you the code here. And what this is just like before we had ml.nodeclassification.train. Now we have ml.linkprediction.train. I'm going to tell it, here's my in-memory graph, my Marvel link prediction data. And I'm going to use those splits I just created, my appeared with train graph and my appeared with test graph. And just one thing to note is you don't have to use our split functions, right? You could split the data yourself, just like I was doing in the beginning with my holdout set. You could do those splits yourself based on expert information and just supply those as the train and test relationships. I'm going to go in and call it, I'm going to generate my new model called LP appearance model. It's going to use my fast RP embedding as its only property to learn on. And again, we have these different properties of how we do the model cross-validation. And then I have a bunch of different parameters that I want to try out different models on. And so internally, we have our test data and our train data. We're going to build models for each of these parameter combinations. We're going to generate those positive and negative sets. balanced internally. And we're going to kind of use our holdout data to predict relationships. Whichever model performs best is the model we save. And so you'll see I'm going to return my best combination of parameters as the winning model, and my train graph and test graph score. And so I'm going to run this. This is going to take a little longer than node classification, because if you think about it, Amy mentioned data sparsity, right? So one, there are a lot of relationships in this graph, right? It's like 55,000. So we've got 55,000 positive relationships. We also have way more negative relationships than positive relationships, right? Most characters in this graph do not have edges between them. So we are learning on a much larger set of data to make this predictive model. So it's going to take a little bit longer. But when you're building link prediction models, it's always important to think about, data sparsity. And just like I rebalanced my data for node classification, we're kind of internally using a different metric to select models. It's the precision recall curve, AUC, to pick the best model. And then as soon as it's done, it's going to tell us, here's the best performing model out of all the different models we tried. And just other things to note is this is pretty simple. I didn't want folks to get lost in the syntax, but you can do other cool stuff like add a link feature combiner. So if instead of just saying, here's my pair of nodes, here's the embedding of node 1, here's the embedding of node 2, I'm going to learn on those. You could say, here's the page rank of node 1, here's the page rank of node 2. I want to combine these using like an F1 normalization. So really cool stuff. So I've trained my model. It has a train graph score of 0.66, test graph of 0.67. This is a demo, so I'm going to be happy with it. If I wanted to, I could tune it to try to make it better. But now that I've trained my model, it's in my model catalog. The next thing I want to do is predict my relationships. So I'm going to go in, I'm going to take my predict relationships. I'm going to take my in-memory graph, and I'm going to make a prediction. So I'm going to tell it, predict using my LP appearance model that I just trained. And remember to filter out the existing appeared with relationships, right? I don't want to predict people who I already know appear with each other. And what I'm going to use is just add a new relationship to my in-memory graph called appeared with predicted. I'm going to add that data back to my database because maybe I want to use it later on. So I'm going to go ahead, run this. And this is just going to run these two queries, update my database. And then as soon as it's done, I can run a query to check who's in my next blockbuster movie. So it'll pop up as soon as it finishes. And then, so that's done. So the final step is we're going to check our predicted links. And I'm just going to go ahead and run this right away. And so just click here. Sorry about, there we go. I've run it twice. So we're predicting the links. We'll see two tables showing me who's going to appear together. And remember, I've just added a whole bunch of different relationships to my graph. So what am I predicting? It looks like I am predicting some kind of like superhero mashup. I know Electro is a villain. I've got Lucifer appearing with Electro, some kind of super villain mashup in the future. I can see a whole bunch of characters. I've got Nick Fury appearing with Electro. And if I scroll down, I didn't only predict folks are going to appear with Electro. That would be a really boring model. If I scroll to the bottom, maybe this is feature 1. We've got everyone appearing with Electro. In my next movie, I've got a whole bunch of people appearing with the Flash. So I have predicted based on who's appeared together in the past, who's going to appear together in a future movie. And if you have a real data set, you can think about the possibilities are really endless. So with the demo done, I'm going to pass it back to Amy.
So thank you. I only regret there are no space owls.
Sorry about that.
That's okay.
Should have added one.
So what Alicia's just walked you through is basically what's the process for having machine learning workflows inside of Neo4j and using supervised machine learning. We started off with loading our data and creating some features using either queries. Well, actually, we use some queries. We use some algorithm results, and you can use the embedding. So Alicia showed you fast RP as well. So creating your features and then training your model. And that was the part where we selected whether we wanted a node prediction, or no classification prediction or link prediction, then selected kind of the properties we wanted to use, did the training, and then the model selection was done for us, the most predictive model. Then you saw it inside of the model catalog. And at that point, as a user, you have a couple choices. You can either publish it and share it with somebody else at your organization, or you can actually just go forward and use it, either on existing data or new data as it maybe gets added to your graph. And then you do something with it. You might want to make just a prediction and then make a decision to contract with the top Marvel actors for the next movie, or maybe you write back to your graph to do other analysis in the future. So it can be cyclical as well. So those are the steps that Alicia walked you through. And just to kind of summarize why, again, you want to use graphs for your graph data science is that you can get better predictions with the data you already have. I think we talked about that earlier. A lot of data science models ignore that network structure, ignore those relationship features, and we know they're predictive. And so adding them to what you're already doing can increase your accuracy and reduce your false positives, and just see things that you otherwise wouldn't be able to do. And so it's a very nice workflow. A lot it's been automated, thank goodness for me, that they can help you from making mistakes with trying to add relationships to what you're already doing. And then we have a lot of customers doing this. And one of the points I like to make is that you can talk about, you don't have to be a super expert, and that's why we have the GDS library and these functions. You can do very simple graph analytics, or you can get to very highly sophisticated graph data science as well. And so there's a couple customers we have that we like to talk about because they span a different spectrum from analysis that are maybe a little more simple ad hoc to something that has to be more advanced, has a lot of complexity, or has to be ready for full production, has to have that robustness and be able to integrate. And Boston Scientific is a great example of kind of more of an ad hoc, where they're doing a lot of graph analysis. They're trying to improve production reliability of their equipment, and looking at and doing a lot of queries of their supply chain knowledge graph. Another example, I guess, on the, I would say the most complex side or the more complex side would be like AstraZeneca, where they're looking at journey analytics. They're trying to improve patient outcomes and looking at how customers change and how patients results and outcomes are different over an entire path, over a journey, and incorporating graph embeddings with that. And then we have a lot of financial services customers as well that maybe don't have quite that level of sophistication in their analysis that they need, but they have to have something that they can put into production with kind of an auto, both with graph feature engineering and auto ML as well, and have that work every day consistently in a production environment. So those are three examples. I think, Alicia, you have a little more detail on some of these that you wanted to share.
Yeah. So I like to kind of, we've shown you a demo about Marvel, super cool. We are not all writing our comic books at work. I like to kind of like zoom back to what's the real world examples. And I think Amy did a really good job of summarizing, right? There's a spectrum of complexity in terms of technical complexity, and kind of, is it you're running things ad hoc, or do you have a workload you're running over and over again? And kind of, if we start at the graph analytics side of things, right, where you're running an algorithm to answer a question, and what you're doing is kind of running these on an ad hoc basis when problems come up. A really good example of that is Boston Scientific. And what they're doing is they're looking for kind of recalls or manufacturing failures. So they make medical devices, including things like pacemakers, stents, and heart valves. And they have a super integrated supply chain. If one of those things fails, it's really bad. So they need to figure out, which things are failing and why. And so they've got their supply chain data in a graph in Neo4j, and they're using graph data science to figure out, given a part that failed, right? And given the components of that part and the components of those components, can they rank, which nodes are most important for a failure? Which ingredients or pieces that went into the heart valve are most likely to have caused that failure? Or if you have some failures, you know what the causes are, running those similarity algorithms to find the vulnerable components. So I had this thing fail. What looks most likely like it? What has the same ingredients? And I want to proactively intervene to stop failures. And they're doing this all in Neo4j. They've got their integrated supply chain data, and they're running graph algorithms basically to say, where do I need to look next? So really an analytics use case. Moving up on kind of sophistication, what I would call graph R&D, where it's super, super sophisticated machine learning tasks, using your connected data, but writing bespoke code, right? Pulling the data out of Neo4j and reasoning about it in custom Python code. This is what I call graph R&D, right? You've got your data in Neo, you're using it to store your connected data in a connected shape, but you're gonna write custom code. Use Neo4j maybe for some feature engineering to help you get data in the right shape. But then what AstraZeneca has done is they store patient journeys. So you've got medical records for people, you have data about every hospital visit they've had, the treatments they've received, the drugs they've been prescribed, when they received a diagnosis over time, where you have this complicated patient journey. That's stored in Neo4j. They pull this data out for patients who have a particular disease and patients who don't have that disease. And they train path embeddings in Python using kind of custom bespoke code to represent each of those different patient journeys. And then what they do with that is they use those embeddings to predict whether or not a new patient journey is someone that's likely to have the same condition or benefit from the same drug. So this is really R&D, right? They've written custom code, they have domain experts working on it, they're making a prediction about which patient's journey looks like they benefit from this drug. So this is like very high complexity, but it's also very bespoke. If you want to kind of combine super complex with something you're running all the time in a production setting, really we see a lot of use cases with production graph machine learning around building better models, kind of what we walked through in the demo today, where what you want to do is add predictive relationships to your production machine learning. So not run a model once and be pleased with yourself, but every percentage of your model accuracy matters for a real system you are using. Graphs are really powerful, but you need to get that into production. So you need a data science platform that can help you commoditize your data science, right? You're going to be building scalable, repeatable data science models, and you need a way to generate features reliably over and over and over again to put into that AutoML pipeline. So what you might be doing here is you've got your connected data in Neo, you're updating it as new data comes in, you run a batch job to calculate those graph embeddings, those graph-based features like PageRank or your hub scores. And then you put those into your predictive model that you've deployed. So you can calculate those features in batches, score your new data, and make predictions. And so really this is, we've moved up, we've talked about custom and super bespoke, we've talked about ad hoc and analytics, and this kind of sits in the middle. And so behind all of this is, again, kind of the Neo4j graph data science framework. You've got your database storing your connected data in the right shape. You've got the graph data science library that you're using to generate features, to do your analytics, or to generate those embeddings or build supervised machine learning pipelines. And then you have Neo4j Bloom, where you can visualize it. If you've got an analyst kind of looking at these predictions or looking at the results of your analytics, they can play with that in Bloom and kind of do the full visualization piece. And just one piece that I've added in, because this always comes up as a question, and I was like, we're just going to have a slide on it, is, how do I try this out, right? Is this available to me now? Can I go get it? And we have a community edition version and an enterprise edition version of the library. But the good news is the algorithms and embeddings, supervised machine learning techniques, those are available in both versions, community and enterprise, as well as our Pregel API, which is what lets you write your own algorithms using the building blocks that we use. So they're super parallelized, they're scalable, they use our graph catalog. You just don't have to learn our internal APIs. So both of those are available to everyone. We want you to test it out. We want to hear your feedback. What we hold back for Enterprise Edition is parallelization greater than 4 cores. So the more, part of what we do when we implement algorithms is we make sure they're parallelized. They're highly parallelized so you can compute on large volumes of data and finish. Community Edition, 4 cores or fewer. Enterprise Edition, more unlimited cores. And this really comes down to how big is your graph. Once you're in production, you probably want Enterprise Edition. Fine-grained security is not supported in the Community Edition, just like it's not supported in Community Edition Neo4j, but GDS Enterprise Edition integrates with that. You've got the model catalog in Community Edition, but you only store one model, whereas Enterprise Edition offers unlimited models. Model persistence and publication, so saving my model, publishing it to my team, is an enterprise-only feature. And our new low-memory analytics graph format is also enterprise-only. So really our focus is everyone should try it out. If you've got a small data set, you're good to go. As you move into kind of these enterprise-grade workloads, we have a second tier of features to help you move into production. And with that, we just want to kind of point you at a couple of references. We've got some really good developer guides. If you liked my demo, we have developer guides for node classification and link prediction that have just been posted. We also have developer guides on tuning your embeddings and kind of the topics we didn't get to today. And you can go to our GitHub to download our code. And of course, Amy already talked about our fabulous books, which are a great way to get started.
Great, thank you. And I think we're running a little short on time, so we will follow up on questions. And thank you everybody for joining. Thank you, Alicia, for the really cool demos. It was a lot of fun. And we'll see everybody later.
Awesome. Thank you for joining us.